Hello and welcome to the English translation of the talk Why 3D printed clothing is not the future. Your translators for this evening are
Duckman
and Mary.
Kein Wunder, ist ja auch ein Fachthema, deswegen seid ihr wahrscheinlich auch alle hier. Zweite Frage, wer von euch hat schon mal versucht, Kleidung 3D zu
Second
drucken?
question,
Bitte erneut Handzeichen.
So questions are who knows about 3D printed clothing and who's done that before actually at home.
Mäßig. Ich sehe eine
So there's
Person,
not a
die
lot of
versucht
not a
anzuzeigen,
lot
dass
of
es super gelaufen
people
ist. Die
who've done
anderen
that
sagen, ja,
before.
mäßig bis gar nicht mal
And
so gut.
if so,
Wer von
it
den Leuten,
didn't
die
work
sich am Anfang
too
gemeldet
well.
haben, dass sie schon mal was in 3D
But a lot of
gedruckt
people
haben,
have
schon mal
3D
darüber
printed.
nachgedacht, Kleidung
Who of
3D
them
zu
have
drucken? Bitte
thought
aufmachen
about
dann.
printing
Also
clothing
nochmal
actually at
deutlich mehr. Wir
home?
sagen vielleicht so
So
10
about
Leute
10
haben darüber
people have
nachgedacht.
thought about doing
So,
that at
unsere
home.
nächste Speakerin,
And
Rebecca,
our next
wird
speaker,
euch
Rebecca,
sagen, warum
will
oder warum das
tell
vielleicht
you
gar nicht so eine
now
gute Idee
why
ist,
that
Klamotten in
might
3D
not
zu
be the
drucken.
best idea to
Rebecca ist im
3D
Internet,
print
vor
your
allem auf
clothing.
Twitter unter dem Hashtag, unter ihrem
You can
Nickname
find Rebecca
Kurfürstin
on Twitter
bekannt.
under,
Und Rebecca ist
using her handle
Bekleidungstechnikerin, das
Kurfürstin,
heißt, sie forscht an der Schnittstelle zwischen
and
herkömmlicher
she's doing
Bekleidungsherstellung.
research
Das heißt, sie hat schon
at
als
the
Sekretärin
intersection
gearbeitet,
between
aber auch schon am Theater und an einer
usual
Fernsehserie.
clothing,
Und auf der anderen Seite
the
beschäftigt sie sich auch mit
manufacturing
innovativen
of
Techniken
usual
wie
clothing,
3D-Druck
like
und
everyday
virtueller
clothing.
Bekleidungssimulation.
And
Das heißt, sie beschäftigt sich
she
auch
also
damit, wie man
does
ein Computerprogramm
a lot of
beibringt, das ein Rock
she
realistisch
does the
aussieht und realistisch
technical
an einer
virtual
virtuellen Puppe klemmt.
clothing.
So, und jetzt wünsche ich euch ganz, ganz viel Spaß mit dem Talk.
So have a lot of
Dass ihr viel
fun.
lernt, viel
Enjoy the
Spaß habt
talk.
und
I
bitte
hope you're
begrüßt
going to have a
unsere
lot of
Speakerin
fun.
Rebecca mit einem ganz,
Let's
ganz großen
greet
Applaus.
Rebecca
Vielen Dank.
with applause.
Dankeschön.
I just received post, but I'm not gonna let that stop me from doing my talk. Welcome to my talk. Oh, more posts. There's a lot going on that stage right now. I'm gonna read that later, but I'm happy that the post office seems to be working well. So my talk is called Why 3D printed clothing is not the future. And I'm going to talk about what makes 3D printed clothing and why it's like that and what needs to be done to make it everyday usable. So I'm a clothing technician, which is maybe a weird combination of words. So when clothing is manufactured, on the one side we have the design, the idea, and to put that into a real thing, that's a whole different thing. So, for example, we have a person who comes up with a design, they design a dress and have a nice picture of it, you can see some things, but not too much, and they go to production, to a company, and tell them, make this dress, please. And they're like, okay, how? We need a lot of information to do that. And everyone's like, what? And yeah, that's where it stops, because the production needs to know what kind of fabric do we need, what kind of sizes do you need, how many do you need, how many in which size, what kind of machines do we need, what to put on the care instructions, how far is the distance between different parts of the dress. And that's where I come in, like I'm in between the design and the production. So I kind of do the reality check. What can be done? How can it be done? So it's a lot about materials, about quality, where to produce it, prices, when to produce it. All of these questions have to be resolved, and that's what my job is.
So I applied this reality check. How can this even be done to 3D printing? And if you have a look in the internet for 3D printing and clothing, then you can see all these headlines about some news. Ooh, 3D printing will bring a lot of flexibility into the fashion industry, or clothing of the future, or is the streetwear of the future from the 3D printer, or can the 3D printer completely revolutionize fashion? A few years ago it was even worse. Oh yeah, 2020 we'll all have a printer at home, and in the morning we'll print a pullover, and in the evening we'll melt it down and print a new one. But they got a bit careful over time. But you can see even from these headlines that there's a lot of hope involved here, that something may change radically, that the fashion industry will be unrecognizable, and there's a lot of sustainability in there, and sustainability has become a big topic in the clothing industry, and, well, I'm going to talk about that. 3D printed clothing actually exists. It's nothing new, nothing special, not completely unrealistic. There have been complete fashion collections that have been 3D printed. I'll show you 3 small examples. For example, the creations of Dani Peleg. Her final collection in Israel was made completely via 3D printer. It was a 5-part collection. There's, for example, this 2-part ensemble to the right, a top and a floor-length skirt, and the skirt was printed completely with desktop 3D printers, which means it's made of modules that have about A4 size, and they're stuck together to form the skirt. The special thing about it is that it moves very well and is very flexible because it's made from flexible filament, but also because it has this zigzag structure that enables the parts to move over each other when you pull on them. It really jumps and puffs up a bit where you pull on it. The jacket you see there is the first 3D printed, ready-to-wear piece of clothing that you can order online. It's limited to 100 pieces, and if you want to buy it, you can do that for $1,500. You can make some decisions like change the color, put some writing on the back, and then it takes about 100 hours to print, and then you have a jacket. Another example is from the design collective Nervous Systems, the kinematic system. It's made out of triangles that are stuck together with hinges. So the whole surface is flexible, it can be moved, but it's made from hard material. So there's like a hard, solid plastic. It moves, it rattles a bit if it moves, if you run. And after a while, they made a version that is proof against spying eyes. The dress on the right is made of these triangles, but has little flower petals printed on it, so that it can't be looked through. The third example is this. It is the pangolin dress. It's made of a structure of different modules that can move into one another and overlap when moving. And that allows limited flexibility. So you can move in this dress and the surface will follow your movement. Travis Fitch was working on this, designer working in New York, and I talked to him a bit. I am a clothing technician. I asked, yeah, can I have numbers? And where do you even get the information that these structures can be used for a dress? What makes you say, yeah, okay, this is elastic enough to use it as clothing? Do you do lab testing? And he was more like, yeah, I pull on it and it's either good or it isn't. And so then the clothing technician in me sort of burst through, and I thought, hey, what about numbers? And so I offered him to examine these structures, do lab testing, to find out what's behind all this. What are the aspects of this in numbers and units? How can you express that? So those were 3 of many examples. At fashion shows on the runway, there are a lot more. And it's, of course, clear that these aren't exactly everyday examples. These are clothes for a special occasion, custom made, can take months to build, made of 300 whatever parts that have to be stuck together. But the question is, will this revolutionize fashion? So that obviously has to apply to everyday stuff. custom fit stuff at fashion shows does not directly revolutionize everyday wear. So my question is, what does this clothing have to do or have to be able to do to be everyday wear that we can wear literally every day and for every occasion? And to me, at this point, it's the most important part is that clothing has to be comfortable.
We can express that through comfort, wearing comfort. There's the psychological part of that, which is about trends and individuality, and that I'm kind of individualizing myself. Wearing a hoodie might fit here, but at maybe a more different context would ask for different clothing. And so in this context, you might feel very comfortable in one kind of clothing, which you wouldn't wear in a different context. And that's the psychological part. Then there's the next to skin comfort. It can be soft or kind of itchy or scratchy. It can cause allergic reactions. There's the physiological comfort, which is about the climate, kind of like your body climate. It has to keep you warm, but at the same time, it has to transport your sweat kind of to the outside, and so it can.
This evaporation must happen through the clothing, and some clothing does this a lot better than others, and it's important for us being comfortable in our clothing. And the fourth aspect is the ergonomics of the whole thing. That's mostly about freedom of movement, and that's kind of the thing I focused on. And the freedom of movement comes, on the one hand, how the clothing fits, how tight, how loose it is, and secondarily through elasticity of the material used. And that's extremely important, since there are parts of the body, for example, the knees and the elbows, where you have to have a stretch of at least 50% if you want to perform any sort of useful movement. And to do that, the clothing has to be elastic and not break. If the material used in this place is not elastic, then the surface would either bow out or distort. So if you have a very tight sleeve and the material isn't elastic, and I do this all the time, then it'll sort of take that shape at that point, and it won't look nice. So we need a material that sort of springs back into its original shape once we straighten out our arm. So if the surface isn't elastic at all, it isn't actually that good for clothing uses. But you can compensate for this with cut. If the piece of clothing is wider, the lack of elasticity is not as significant. So my question was, how can I find out how elastic these 3D printed structures are? If I can do that, then I can use them consciously in a targeted way to significantly raise the ergonomics and comfort of 3D printed clothing and bring it closer to everyday usability. And if you look at textile surfaces, like the ones that we wear every day, they implement the elasticity. Then there's two aspects. The material itself may be elastic. It's usually called elastan. It's awesome. You can stretch it by 300% and it will spring back. And it's used in many, many pieces of clothing. So a usual mix ratio is 98% cotton, 2% elastan. And those 2% are enough for the shirt to be movable enough to get in there. It can be very tight, but it won't deform or anything after wear. The second option is via structural elasticity, and that is usually done via weaving. And if you pull on a surface, then the threads will move, and they will move relative to each other and distribute a bit of their thread to their neighbors. And that, in combination, makes an elastic surface with material that isn't all that elastic. Cotton fiber, for example, isn't elastic at all, but if you weave it the right way, it's a very movable and elastic surface. And if you transfer this to 3D printed surfaces, then you can use an elastic material here, for example, TPU, that's thermoplastic polyurethane, and polyurethane is used in elastan. So it has very similar aspects, and because it is based on the same chemical ground rules. Structural elasticity is possible via, you can print a weave, but you can also use other shapes such as arches, spirals, springs, things you can compress or pull on, so that at first you distort the structure and not the material. The kind of things you can do with that depends on your printing technology. There are different ones, and not all are the same for making fashion. For my research, I specialized on two processes.
So for the one, on the one hand, I did the FLM, the method, which melts filament. So it's thermoplastic. So it's heated up, and then it melts, and it's liquid, and then you can design a geometry using that. And if you have an object with that kind of hangs over, like you see on the left, you need some pillars to help that stand, and that structure, like the pillar structure, needs to be built from the beginning and is in the finished object, and you have to remove it afterwards. That's no problem. If it's a hard enough material, you can just break it off. But if it's elastic, you can't really break it off. If you pull on it, it just elongates, and you don't really win anything. So if you try to build geometries like that with an overhang, that method doesn't really work for it. You don't win any time or get anything out of it, out of the method like that. I didn't catch.
Good idea, but it doesn't work with TPU. For other technologies, you have BPA, which can be dissolved in water, but those structures don't really fit together. TPU needs a very high temperature to melt. I printed that stuff at 215 C, but the PVA already started decomposing from the temperature. So theoretically, a good idea, but right now what's possible with these printers, it doesn't fit yet. I am of good hope that something new will be developed, but yeah. The other process is SLS, selective laser sintering. It's a powder-based printing process where you put layers of powder into your build space and use a laser beam to melt the grains of the powder together where you need your geometry, and then you add another layer of powder and so on. So the powder itself is your support material, and you can do away with all those columns. At the end, you have filled your complete build space with powder, and somewhere in there is the structure you printed. And that powder can be easily removed later and reused. For my research, I tested a variety of different structures. The left and the center one are made with SLS. So I had the possibility to add a bit of height, to chain things together, and I did that in different sizes, the larger and a smaller variant, and the smaller variant is obviously a lot more mobile. You can really fold that up nicely and move it, and these little modules can be moved relative to each other. You can push them together, and that makes it all very mobile. With the other process, I was limited in my design choice, so it's a bit simpler. This one is based on a diamond pattern that has been extruded into three-dimensional space. And at first, the diamond structure is stretched before the material actually moves. I had this with different variants, big diamonds, small diamonds, different layer heights, to see which variant has which elastic properties, so that it can be decided which factor is the deciding one for the elasticity values I get. How can you even test these values? By pulling on it. You take a sample strip, something like this, put it into your testing machine, and the machine will pull on it with a constant speed. But the software that works with the machine spits out a little diagram. You can see it on the right. And the diagram shows you the change in length in percent, so how much it has been distorted, and the force used. So you can use the diagrams to how resistant the material is against tearing and how much it can be distorted without springing back and spring back. Stretching and elastic stretching is not the same thing, but if I pull on something and I stretch it, it's going to keep its shape because I overstressed it. But if it's elastic enough, it will spring back into the original shape. Those are two different numbers that can both be derived from this diagram. I did that with all my different variants. And of course, you have to do multiple samples and average them out and everything. And then I got numbers and units. And so I had these numbers. So one thing I have to know is, are those good numbers? Are those bad numbers? And for that, there's a recommendation by Dialog Textil Bekleidung, together with the German Fashion Association. It's not an international standard, it's not a law. So clothing doesn't have to reach these values, but is a recommendation how clothing should behave and what forces it should be able to tolerate. This is a small part of that, split by product groups, like pants have to survive different things compared to underpants, and if it's a bit looser, then you need less pulling force, because if it's further from the body, it's not important how much is pulled, it doesn't have to conform as well. So I compared these numbers and found out the amount of force needed to permanently distort my structures was okay, but the maximum force before failure was not okay. So I can pull on the thing, that's awesome, but it's very easy to pull too hard and rip it apart. So yeah, they are flexible, but the forces, if I move my arm and the thing rips, then the piece of clothing doesn't help me much. These 3D printed structures are limited in that sense. Then I want to have a look at the factors that actually cause this to be elastic or not, or how much. And what I saw from my numbers is that the size of my elements did have an influence. So the larger variants had better values than the smaller ones, but the big ones don't really look or feel all that much like fabric. But the small ones are closer, but it didn't get as good numbers. And then there was another factor, which was the slicing program. And the slicing program has two significant jobs. First of all, it splits my 3D object up into layers. And second of all, it tells the 3D printer where it's supposed to be in which layer with the print head. So if you print a vase like this, the lowest layer will be completely filled because you want to pour water in there and it's not supposed to leak out. So the path from the printhead, or the path of printhead could look roughly like this. It would go back and forth in rows to fill everything completely. The second layer would be a ring, and the printer might be doing something like this. Maybe it will take another path, though. There's a lot of different programs, and they are limited in their configurability. And I had a closer look at it and saw that with my diamond structures, the printhead took a fairly particular path. It went over to this crossing and then back in another direction. Under the microscope, you can see that it tore exactly here. The printer didn't actually traverse the crossing, so all the strands are just ever so slightly melted together. Whenever a new hot strand came their way, it sort of stuck to the other. But the strand didn't actually bridge the gap, so that's sort of my point of failure. And that's where it tore apart. In another variant, which is based on basically the same pattern, the slicing program decided to do it differently. It decided to go right to the bend in the middle of the diamond. So, of course, the fracture point is now there. And the samples look different because they tore in a different place. And that explains my low yield strength, because I'm not actually pulling on the solid material, but on the places where it's just sort of stuck together a bit. And depending on how well that happened, this can be easier or harder.
So the method itself already makes the strength kind of low. So I've tested 8 structures using different variants. So you could ask now, how do you come up with the idea that now 3D printed clothing isn't a good idea and that other things might be better? And I say, well, could be, and depending on the method you use, there's boundaries to how far you can get. So here we have to take a closer look actually onto molecules, on the molecules itself. So different strings have different
They have different tensile strength due to the way the molecules are arranged. So we have either amorphous or crystalline areas, and that's the squiggles to the right. They are supposed to be chains of molecules, and where they're sort of tangled together a bit like a plate of spaghetti, they're not exactly that stable. In the areas where they're very ordered, they are very solid. And the natural fiber have a tendency to be, or to have a high amount of internal order. Many crystalline areas, they are very solid. They have a high tensile strength from the get-go that my structures do not have. And if we're looking at synthetics, then you can influence how hard they are to tear. There's different technologies to make fibers, and at least one of them is very close to 3D printing, in which you liquefy or the plastic or the material that you want to use as a fiber, and you press it through a nozzle, and it turns into a fiber there. It's very similar to 3D printing. The difference is that you can influence what properties the fiber has at the end. The degree of crystallization, so how much of the thing is crystalline, is dependent on how fast it cools. The slower you cool the fiber, the more time the molecule chains have to go into an ordered state. So these spinning machines are heated to cause the cooling to be as slow as possible, to get a degree of crystallization that is as high as possible, and hence a tensile strength that is as high as possible. We do not have this possibility with 3D printing. We can use a heated print bed, but that only influences the first 1 or 2 layers maybe, and nothing after that. And after the strand has been deposited, we want it to harden as fast as possible, since it might just run off to the side, and we want to have a certain geometry that we decide we want it to have. it's not supposed to flow apart once it's been printed. And when the next layer is added, well, that only works if the layer below it is already hardened. So we can't just keep the thing at a constantly high temperature all the time. With SLS printing, it's a bit different. It's better for making high tensile strength materials, and the structures had significantly better results as far as tensile strength goes. With synthetic fiber, we have another possibility, which is stretching them. After they've been spun, they are shoved through rollers, and these rollers pull on them, apply a pulling force, and that raises the degree of crystallization. Because the molecules are aligned and forced to align to each other, this also leads to the fiber becoming slightly thinner, and it becomes finer, softer, but more solid. That explains why textile fibers are so much more solid than, but still much finer than what comes out of a 3D printer. Textile fibers can also warm you very well by trapping air for insulation purposes. You get these little chambers due to the weave, and those can warm us. And that's because textile surfaces are made of threads. These threads are made of fibers. And as you can see on this microscope image, this is not some rough carpet. This is a microscopic image of a very small piece of cloth. You couldn't even see this with your eye. But in all these little holes, air can be trapped, and you'll be warmed by it. The small distances are also important for transporting moisture, because sweat can evaporate and go through them, so the clothing can warm you and protect you from overheating. And small fine structures like this can't be made by 3D printing. We are very limited in fineness, and we can't just print tiny air chambers. We're still quite limited in that.
So there's a couple things that 3D printed structures just can't do. But there's other things that they can do. So we have a lot of freedom of choice when we design a thing. So things like bracelets or necklaces or glasses, we have a lot of freedom to design that. Or for costumes in the movie, for example, Black Panther, they 3D printed the crowns, which is one example what you could do with that method. So you only build up material where you need it, which is very sustainable. In normal clothing manufacturing, if you cut a pattern from fabric, you usually have like 10% loss of the fabric, which is not a good thing. You lose a lot of fabric there. So this is one of the good aspects of 3D printing clothing. And you can actually recycle the materials very well, which is another downside of the normal clothing industry. It's very well suited to fabricate individual pieces, one-of-a-kind pieces, and you can have one product with different properties in different parts of the clothing. So you could make it thicker, for example, around the shoulder if you want it more stable there. And if you would try to do that with the usual way with fabric, you would have to use different fabric there or added fabric. And you couldn't just print it in one go, like the 3D printing.
You could also integrate cables, LEDs, some sort of sensors. But, well, there's a question mark behind this because it's not really everyday stuff. And we can't yet get that in such an advanced state that it's standard. One advantage could be that you can make the entire piece of clothing in one single step. Right now, you have to first make the fabric, cut the fabric, sew together, maybe dye it. Those are all different steps happening in different places. And if I 3D print a piece of clothing, then I could just do it in a once-through process, but only if it actually fits into the printer's build space. So if you print an A4 sheet and stick many of those back together, then we're right back where we started, where things have to be built out of components. Something a bit more complex is this thing Nova Systems developed, which is a software that digitally folds the dress and it is printed in a folded state, which reduces the build space significantly. So somewhere in this powdered block you have the dress, and you have to sort of archaeological free it from the remnants of powder, clean it and unfold it. But it's a nice way of using the advantage of 3D printing of everything happening in one step. But aside from that, I still see significant problems. There are also disadvantages or challenges, such as the tensile strength or lack thereof, which is a feature of the process itself. We're limited as far as fine structures go. So the standard nozzle diameter is 0.4 millimeters, and with fibers we're looking at micrometers. Those are significant differences. And fineness is important for how something feels on your skin, for transporting moisture, for warming via entrapped air. And that is so elementary that these four aspects of comfort just are not happening if the piece of clothing is 3D printed. Time and cost is looking very bad. It takes quite a long while to print, and it's very expensive. So this isn't every day yet. This is custom jobs. How to wash or clean one of those things is has to still be determined. How you wash it. And if we're talking about clothing, we have to talk about how do you close it. You have to get in there somewhere, so there have to be zippers, buttons, hooks, eyelets. You have to think about that sort of thing if you want to print the whole thing once through. So building fabrics from fibers, from threads which are made from fibers, right now is not to be beat as far as comfort goes, and there are no real solutions for imitating it, either via 3D printing or some other process, or some other arrangement of material in a different way. This hasn't been solved yet. That means that right now, state-of-the-art, 3D printed clothing is not only not the future, but not even today, because today our stuff is made of textile fibers, and it works really well, but 3D printed structures just can't do that yet. That doesn't mean we should stop looking at the problem, and whoever said that would work well, I'm interested in what worked well, and if there are maybe other aspects involved that I didn't think about here. But it shouldn't be forgotten that the basic function of clothing shouldn't be forgotten. This art I showed in the beginning is awesome, and I think it's the best thing ever, and research on that sort of thing should be done, but clothing is supposed to warm us, and it's supposed to protect against prying eyes, and it's supposed to keep our body climate optimal. My hope that with a sustainable process we could maybe revolutionize the entire industry, or through that we could do that through new production processes. That's a bit problematic, since the fashion industry is highly problematic. There are many problems, ecologically, societal problems. And putting your hope in a new technology and saying, yeah, this will solve everything because it's sustainable, and then we're just going to print everything with a 3D printer, and the sustainability problem will be solved. Yeah, I'm not seeing that. So yes, please do the research, but don't forget the basic function. And don't just sort of rest on your laurels that this new innovative technology will solve everything. So revolutionize the clothing industry in all other aspects as well, and don't depend on 3D printing solving all the world's problems. And I'm done with my presentation, and thank you for listening. This has been the C3Dingo English translation of the talk, Why 3D Printing is Not the Future. Your translators were
Mary
and Duckman.
Das war eine ziemliche Punktlandung. Wir haben leider keine
For your
Zeit,
information, there will be no Q&A since this talk ended basically at just the right second. You can ask Rebecca things on Twitter, for example, at Kurfürsten, and you could probably catch her somewhere after the talk. As far as the translation goes, we accept feedback at the email address hello@c3lingo.org, or you can Twitter using the hashtag C3.